Hello and welcome to another episode of the Omics Casts. Today we're going to talk about MGS, BGS, NGI, BGI, CoolNGS versus SBS. This episode of the Omics Cast is in reaction to a tweet by James Hatfield, who goes by Core Genomics on Twitter, where he describes with some very good detail information about this CoolNGS chemistry that the company MGI or BGI is putting together. They presented this recently, and it's an evolution of what they currently have, which is on the higher end of their platform offerings, the T7 machine, what they call the MGI T7, which is a machine that can produce up to 6 terabases of information per run, and the runs take about 24 hours. These are on designs of between 1 and 4 flow cells that can run separately, and different flow cell densities that can generate between 1 and 6 terabases of information per day, right? And so this T7 machine, which generates 6 Ts, I'm kind of inclined to think that they can get up to 7 Ts, and that's the reason why they called it T7. But commercially, they can support up to 6 terabases. Is a machine the size of a very large freezer or very large fridge that is MGI or BGI responds in China to what Illumina has done with the NovaSeq and the S4 flow cells, where they can generate 6 terabases over about 48 hours or a bit more than that. And so similar technology to what the Illumina company is doing with the SBS sequence by synthesis technology, and similarities as well in the way the information is captured by taking high resolution pictures of the flow cells as they go cycle by cycle. And so what has happened recently in AGBT 19, a conference that takes place in Florida in the US, is that not only they presented the T7 system, but they also presented this new CoolNGS chemistry, which uses nucleotides that are not fluorescently labeled, which may enable them to get around the core SBS patents. So this is important in the sense that it's a technology that will put them further away of the current technology that's being applied in Illumina platforms, the sequence by synthesis technology. And it's interesting as well because they think it's a cleaner technology that has more potential for improvement. So what is CoolNGS in a succinct way? It's still sequencing by synthesis in the sense that you have a template molecule here depicted on the left, and then you incorporate the primer is the bit that guides what the polymerase is going to do, and then you incorporate one base at a time, here shown as a T, for each of the cycles that you apply to this molecule. And so it's a cycle-by-cycle technology that here they've modified in a crucial aspect. And what they've done is, instead of attaching these modified nucleotides that have a fluorescently labeled molecule, a fluorophore, what they have is that they have this blocker or block-dependent modified molecule that does not fluoresce. It cannot fluoresce because it doesn't have a fluorophore. But these molecules can be recognized by another molecule that does have a fluorophore. And here what they use in the CoolNGS technology is an antibody. Same antibodies that you have in your body, and that react if you have viruses, for example, from a common cold or from the flu, and make sure that those are mopped up. Antibodies are, very powerful molecules, and it's one of those things that even at the physical level, the capacity of these molecules to recognize with very high specificity other molecules is astronomical. And so we have a lot of technology developed in the last 10, 20 years to produce antibodies that can recognize something very specifically. And here what BGI is doing is using antibodies that selectively recognize A, T, C, or G, and as you see in these 4 colors. Then when this cycle has completed, meaning the molecule has attached, this antibody has a fluorophore that can emit light, and then it can be measured by the picture that is taken. Then once that has happened, it can be washed away, and then this blocker that is here with the blue line can be taken out so that this turns into a normal nucleotide now, and then we can go into the next cycle. So the next cycle is at the beginning of the picture, where we incorporate another nucleotide, and then we bind a nucleotide with a fluorophore attached again, etc., etc. So this is different from the Illumina SBS technology because the nucleotides don't have to have a fluorophore attached, right? And these fluorophores can be washed in principle using this CoolNGS technology very efficiently, and they don't linger around in the flow cell. One of the reasons, speculated reasons why the Illumina technology cannot reach very long molecules is because once you've done enough cycles, the fluorophores linger in the flow cell, and they just make everything a little bit fuzzier. The recognition of each of the cycles and each of the clusters a bit fuzzier as time goes on. The argument here from the CoolNGS technology is that this washing of these antibodies, because it's not covalent in the nucleotide, it can be washed very efficiently, and then so you have a cleaner process as you add more cycles into this process. How much cleaner? Well, it's difficult to say currently because this is still in R&D. They're still doing the tech dev of this technology. They just presented a little bit of it at AGBT 2019. But they say that they see potential to go from, instead of going from a per-n 300 cycle run into a per-n 600 cycle run, so double the amount. And they see that the single N 300, they can turn it into a single N 800. So a single N 800, meaning if they can do 800 cycles of this CoolNGS technology, they can sequence molecules that are 800 base pairs of consecutively sequenced nucleotides. So room for improvement, as you see from where most of the technology is now, and the T7 is around here, and the Illumina NovaSeq is around here, even though Illumina with their S prime can do better than this already. But at a large scale, generating several terabases of data per run, they think at BGI that they can go much further with their CoolNGS technology, right? So we explained why this is potentially useful on the technology side. How much will this impact human resequencing of genomes, for example? Well, it depends. I mean, how long is too long, or how long is long enough for NGS sequencing to be of better quality, higher sensitivity than we've done in the last 10 or so years with Illumina technology, with a 2x150 base pair reads. Where does it matter? It matters in the repetitive regions of the genome, because they're repetitive regions, there are many of them, and they are interspersed in the genome. If the repeats are long enough that you cannot distinguish within them by sequencing a molecule inside the repeat, then you cannot confidently map what's inside, right? And so if you had NGS molecules that were longer, you could bridge over the repeats, the left-hand side upstream boundary and downstream boundary of the repeat in the chromosome, and then you would have a lot more sensitivity to do that. We know how well this can be done in long-read technologies. For example, Oxford nanopore, they can do several kilobases, and there's people that even do beyond megabases, megabase pairs, meaning 1 million or more consecutive bases sequenced from a single molecule with Oxford nanopore, or PacBio that does similarly different configurations, can do, for example, 50 kb, 50,000 consecutive nucleotides from a molecule, or do multipass, maybe 10 kb or 5 kb, etc. So the human genome has all these repeats. Some of them you see, as you can see here in the lines, there are multi-kilobase repeats. Others are multi-kilobase but shorter, like these transposons, 2 or 3 kilobases. But crucially, there's one element here, which is the SINEs and the allo family, for which the human genome has millions of them, an average human genome has millions of them, for which they are between 100 and 300 base pairs. So some of these you can bridge with Illumina 2x150 or with MGI BGI 2x150 molecules, because even if you don't sequence the bit in the middle, the 2x150 is a molecule of an insert longer than the average allo. But, and this is crucial, these allos are interspersed in the genome and they have so many copies of them that sometimes read 1 and read 2 will fall in 2 allos, right? So you'll have an allo upstream and another allo downstream, and both reads of read 1 and read 2 will fall inside the allos. At that point, unless you have a technology that sequences long enough that you bridge any of the boundaries between those allos, you cannot map them uniquely. How different, how separate are these inter-allo distances? Well, in kilobases here, as you can see, most of them are between 1 and 2 kilobases, with the average at 2.4 kilobases. If you calculate the probability of your reads falling in 2 allos that are dispersed by 1 or 2 kilobases, it's not that high, it's not astronomically high, but it is high for this part of the plot, obviously, and then further along, it's almost negligible. So sequencing technology that can reach close to a kilobase, or can go to further beyond the kilobase, they have an advantage because they can bridge these inter-allo distances much better, right? And so further beyond that, the next level, it's probably the transposons that we have about 300,000 in the genome, and then the lines, line 1, 2, and 3. The lines are much longer, so for this, it's probably going to be Oxford Nanopore or PacBio or similar technologies that are going to be the ones that bridge that gap, right? So we explained why longer reads are important. We explained why this CoolNGS technology seems to have a capacity to do longer reads. Let's talk about another motivation why, and this is explained in James Hatfield's blog post, why MGI BGI may be doing this, may be putting effort in this CoolNGS technology. And that's a patent reason. The patent war that has started between Illumina and MGI. Illumina launched the litigation in 2 different countries in Europe against MGI. And this alleged infringement of 2 patents that are described here for modified nucleotides for polynucleotide sequencing. And this is because Illumina uses nucleotides with a fluorescent molecule covalently linked to the base, whilst MGI CoolNGS could do this indirectly by attaching it to an antibody, right? So here's a reason why MGI BGI may be doing this for technological reasons that I explained up until now, but also for patent reasons for the current litigation with Illumina. Now, MGI has also hit back with a recent lawsuit, which alleges that Illumina infringed a different patent in the US that describes methods and compositions for efficient base calling and sequencing reactions, and describes a 2-color SBS workflow as used on both the NextSeq, which is the kind of mid-range platform, and the NovaSeq, which is a high throughput platform, and probably what makes the most money in Illumina's coffers. And then James Hatfield speculates that if this stands up in court, then expect it to be used as a bargaining chip in negotiations between the 2 companies. So the CoolNGS technology may give MGI some more freedom to operate in their current operations, but they've sued Illumina on the 2-dye, 2-color technology to try and see if they can get around of the countersuing Illumina for what they've been sued so far. So an explanation here of why this may be important. Now, how does this relate to the current customer today? Well, as you know, if compile some information, put it online available for people to see. One of the ways of measuring how different technologies work is to measure the gigs per $1,000 that you can get out of a sequencing experiment, right? And so the Illumina platform, different platforms from Illumina, from the smallest throughput to the largest, is depicted here. And as you can see, this is the number of gigs that you can get per 1,000 genomes and per $1,000, sorry. And if this was a human genome and you set it so that you can sequence about 30 times the coverage of the human genome, then you would be at around the 90 to 100, 120 gigs here. So the 100 gigs mark is a good mark for the the number of bases that you need to sequence if you want to sequence a human genome in its entirety. And so Illumina, for their tiniest of the sequencers, the ISIC 100, they don't reach that mark by far, meaning you can do some targeted applications there. But then as you move along the higher and higher throughput of the bigger machines, you can go into the MiniSeq, the MySeq, the NextSeq 500 single flow cell here will give you about 1/5 of what you need for a human genome for that price. And then the high-seq machines that have been evolving. And then you reach the point of the high-seq-X. The high-seq-X, as you can see, it breaks this mark for $1,000, which means you can produce a $1,000 genome for you can produce a whole genome for less than $1,000, right? At about, let's say, $800, $900 or $1,000, depending on your purchase, the number of machines, the number of flow cells that you will buy from Illumina. And then the NovaSeq platform, which is the evolution of the HiSeq platform, also has some flexibility in the flow cells that they use. And then the NovaSeq S4 flow cell is also the other one that can also bridge this mark. The way it's currently priced, it's not that far from the HiSeq-X. And so the NovaSeq is very similar in pricing to the HiSeq-X in the sense that it gives you the $1,000 genome, but it's not much cheaper than that, right? So how about other technologies out there? Well, we've discussed the MGI T7. If you apply it to the highest throughput, it bridges this $1,000 genome mark and some more, meaning MGI can probably offer genomes at a similar price than Illumina, sometimes cheaper, but it's not substantially different to what Illumina is already doing. So if they had a problem with patents and they had to pay royalties to Illumina, that would be a problem for them. If they improve their technology and they have some more margin on how much they charge customers for that, then they could overtake Illumina on that side. Now, I don't want to leave this plot without showing what else is in stock here. The PacBio Sequel 2, it's been announced recently, and they claim that they've reached this mark, the $1,000 genome. This is still debatable. I haven't seen customers claiming that yet, and there's only a few places in the world that have this machine. But there's another big player here, and the big player is Oxford Nanopore. And Oxford Nanopore has improved massively in their capabilities in the platforms, and their PromethION on 48 flow cells has now bridged the $1,000 genome mark. And not only that, in some configurations, some people, and there's a group of people in China that have done that, it reaches an even higher throughput than the average throughput of a NovaSeq run or an MGI T7 run, meaning they have a lot of power that they currently demonstrate in customers' hands with the PromethION. And not only that, but also they think they have a path forward for the 10 terabases instrument runs, 12 terabases instrument runs that would put them in places that are easily way beyond where this plot is currently showing. So a little bit about where everybody is and where technology may be going. Who's going to win this race? Who do you think will be ahead in the race, in the NGS race, in 5 years' time, considering how fast Oxford Nanopore is improving? Has Illumina got much slack left in them? who's going to push Illumina to improve? Is it going to be MGI, BGI, or is Oxford Nanopore really the key to this picture? Pacific Biosciences, as you know, the Illumina made an offer that they accepted to be acquired by them, but they need regulatory approval for that, for their possible anti-monopolistic pursuits. And so it's difficult to say. Illumina is a little bit like the Intel, when Intel was threatened by AMD a few years ago, maybe a decade or two ago, where they said, we have a new product in the market. It's 20% faster than the fastest Intel product. And then Intel said, okay, we'll take our tech dev that we have on the shelf. We'll take it from our back pocket. Here it is. Now we have a product that's 30% faster. And then AMD would scratch their heads and say, okay, what can we do to overtake again the dominant player in the market here, Intel? And then they'd say, now we've come back 6 months later, and now we have a product that is, again, 20% faster than the fastest Intel product. And then Intel come back and said, well, now that they've shown what they can do, the fastest they can do, now we have another product that is, whatever, 50% faster. And so Illumina, a few years ago, was improving their technologies from being able to do a $5,000 genome to a $1,000 genome. That's considerably better, and you can say it's a 5-fold improvement. And a few years ago, they already announced that they are thinking about the $100 genome. That's a 10-fold improvement over the $1,000 genome. And they are demonstrating that the flow cells in the NovaSeq, etc., are 2 times, 3 times, 4 times better than technologies that they've developed in the last couple or 3 years, right? So they are in that kind of scale. MGI, BGI, very similarly to Illumina, and they have recently been able to show that they can match the best Illumina technology with their T7, but they don't sell it. They say they may sell it at the end of 2019, and if they cannot sell it outside China because of the patent litigations, they're restricted to the Chinese market, which is a huge market, but it's restricted to a part of the world. Pacific Biosciences, they also making improvements, but they are aiming at being close to where Illumina is currently in number of gigabases they can produce for $1,000. So you could claim that PacBio is a close contender, but they haven't demonstrated a machine that is on par or better than the best machines out there in terms of throughput. Whereas Oxford Nanopore, in the last few years, they've had a cadence of improvements that has been spectacular. And spectacular, I mean a 10-fold improvement every so often. It's difficult to say exactly when, because you can get, bogged down into the details. But if more laws said that you could improve microchip technologies every 12 or 18 months, then Oxford Nanopore, in some ways, their technology is moving even faster than Moore's law, which is what Illumina used to do at the beginning of the technology. And so they have a lot of space to run and to overtake everybody else in this race. So here it is, bit.ly/NGS race. Click on it, go and place your vote, and we'll see in 5 years' time who was right and who was wrong, who do you think will be ahead in the NGS race. I hope you like this episode. My Twitter handle is twitter.com/AlbertoVilella. Contact me on LinkedIn if you want. I'll try to answer any questions you have. Click subscribe if you like these podcasts. And a reminder that this slide deck is available upon request. Until the next episode, I hope you enjoyed it, and see you in the next episode. Until the next episode, goodbye.